Welcome back, students. In the previous video, we talked about refraction. We talked about the refractive index, and then we talked about the difference between the real depth and the apparent depth in a water tank. And we also talked about how the sun appears on the horizon before it rises and after it has set. We said it was all because of refraction of light. Today, in this video, we will talk about a very interesting phenomenon which happens because of refraction, and that phenomenon is called as a total internal reflection. It is not that we are using a mirror to reflect things. Without using anything, light can get reflected back into the same medium. We'll explain how this happens, but this phenomenon is called as a total internal reflection. This reflection takes place because of refraction. That must be surprising to you. Let's take two mediums. Medium 1 and here is medium 2. Okay, this is the interface between those two mediums. Like maybe I have air here and I have glass here. Okay, so this is air. I'll call this as air, and this is glass. So clearly, the refractive index of glass is more than 1. It is roughly 1.5, approximately 1.5. The refractive index of air is roughly 1, slightly more than 1, slightly more than 1.0003 or something, but I'll just keep it as 1. Okay. It is the refractive index is the same, almost the same as the vacuum. Okay. So the speed of light in air is almost the same as the speed of light in vacuum. So that is why you get 1 refractive index. But here that is not so. The speed of light in glass is less than the speed of light in vacuum. So you get 1.5. All that we have already discussed. So this is the interface. Okay. There is, suppose I have a ray, a light ray that hits here, comes and then it hits this surface, and now this air, and then I've kept a glass here. So what happens now is that, so this is a normal at that point, and this is the angle of incidence. The light, if this was not there, if this glass was not there, here, I have glass here, glass was not there, it was purely air, then it would have continued its direction. It's continued its journey undeflected. Okay. But now, because it's entering into a different medium, it's going to bend. Whether it is going to bend towards the medium or away from the medium depends on the refractive index of the medium. If the medium is denser than medium 2, is denser than medium 1, then light will bend towards the normal. If this is medium 2 is rarer than medium 1. So we have two things. One is denser, optically denser, and optically rarer. So here, out of these two, this is a rarer medium and this is a denser medium. Glass is a denser medium and air is a rarer medium. So, if medium 2 is denser, then this light will bend towards the normal. If medium 2 is rarer than medium 1, then light will bend away from the normal. Okay. So, if there is no medium 2, there is only medium 1, then it would have continued in a straight line. Okay, so that is what you have to understand. Now, I've got glass here, I've got air here. So what will happen is that it will bend towards the normal. So going like that, it will slightly bend towards the normal. Okay. And this angle is called the angle of refraction. So we know this. And this refractive index is given by sine I by sine R. So you have to be careful here. So when you say mu, this is a refractive index of medium 2 with respect to medium 1. So this is the refractive index of glass with respect to air. Well, suppose this was water and if this is glass, I have kept a glass inside water. Okay, then it will be the refractive index of glass again with respect to water. Okay, so that would be a different value. For this, what is this actually? I told you that this is actually the ratio between the speed here divided by the speed here. So this is C, almost C, right? Air, that divided by velocity of light in glass. Suppose this was water, then instead of C, you will have velocity of light in water divided by velocity of light in glass. So you will get a different number. So this we have already discussed. Okay. Note here, this is a rarer medium air and it's a denser medium glass. So let me do this experiment. Let's try to do this experiment. Suppose I start from here. I send a light in this direction. The light goes in this direction. Then you see sine I is 0, right? Because it's through the normal. I is 0, or will also be 0. Then we have a 0 by 0 condition indeterminate. Okay? You can't assign a number to it. But for any other angle, then you will have another angle here, and that sine I by sine R will always give you this 1.5 for this combination, air glass combination. Okay, so if I start from here and if I go like this, as I increases, R also increases, but R will not increase as much as I. I will always be greater than R. As you come from air to glass, from rarer to denser. So this is rarer medium, this is denser medium, air to glass. So this angle R will always, in this case, will always be less than I. Angle R will be less than angle I. Okay, so now that you know this, you understand that you always get this 1.5 irrespective of the angle, the non-zero angle. If it is 0, it goes straight. If it is non-zero, then I will be greater and R will be smaller, but you will always have an I and an R. Okay? What happens when you send the light in the opposite direction? In the sense that what happens when light travels from glass to air? What do we expect to do? In that case, this will become I. Okay, I'll do it this way. So this will become I, this angle, and as it goes there, then it will go like that, and then this will become R. So let me start with the same experiment. I am going to send the light ray in this direction, normal. If I send it along the normal, it will go straight without any deviation. So here also, in this case, I have sine I by sine R. You see, I am writing that in red. Black is for this path from air to glass. Red is for glass to air. Okay. So this is going to be equal to the refractive index now. But notice, now this refractive index is the refractive index of air with respect to glass. So this is 1 with respect to 2. You see, it's different. And then this is also equal to 1 by mu 2 1. That is refractive index of glass with respect to air. From this, because see, this is becoming upside down. Okay. And clearly, this sin I is actually, which is the first medium? Glass is the first medium. So it's like Vg, that is velocity of speed of light in glass, and divided by speed of light in air or vacuum. So Vg by C. The perfect definition of the refractive index of a material is this: the velocity of light in vacuum divided by the velocity of light in that medium. Discussed that yesterday. I'm saying I keep using the word air because air and vacuum have almost the same speed of light. So that's why I keep saying that. But the perfect definition, the exact definition is this: the refractive index of a medium is equal to the speed of light in vacuum, where you get the maximum speed, divided by the speed of light in that medium. Okay, so you got this. This is what you got. So now I'll come back to this experiment. So what happens here? I am sending the light here. Then if I send it through normal, then it will go undiflected. It doesn't matter. Doesn't matter like what medium you have. Whether you have air glass, air water, water glass, anything else. As long as you are sending the light through the normal, then it will go into the other medium undeflected. Okay? So this will go straight. But notice, then I make an angle I here. Right? So this is the angle I. Then you see, then I get an angle R. And notice now that this R is greater than I. Okay? So I keep increasing I. As I keep increasing I, R will also increase. But R will now be greater than I. See, in this case, you notice here, R is going to be greater than angle I. When you go from this medium to that medium. So I keep increasing, okay? Then I get a certain angle I, maybe something like this. This angle. I get this angle. Okay. But this angle, suddenly this bends, and this is grazing the surface. From here, like this. I keep increasing here, then this also will, the refracted light will go towards this horizontal, right? It will become, for I, this is my R. I increase this, it will be like this. I keep increasing, so the emerging light will be like this. So as I keep increasing the angle of incidence here, the angle of refraction will be becoming bigger and bigger. Okay. And then there is some angle I at which this refracted ray will be grazing the surface. So it will go here, refracted, and then it will be grazing the surface. And for that angle, then this R is actually 90 degrees. R in this case is 90 degrees. And that incident angle, that I, is actually called as a critical angle, IC. So start from 0 degrees, 5 degrees, 10 degrees, 20 degrees, 30 degrees, 40 degrees, then 45 degrees. Then I see this one at 45 degrees of incidence, then the refracted ray is grazing this. And I call that 45 degrees as the critical angle. It depends on the material, we'll get to that later. Okay. Then what will happen now if you increase the incident ray beyond this critical angle? If I increase this ray beyond the critical angle, suppose I get another ray like this. Okay. So now clearly that angle, that ray is beyond the critical angle. Okay, this is another point. Okay. And greater than critical angle. Okay, and you see. So for this angle, then what happens? Anything for any other incident angle which is greater than IC, then this will reflect back into the medium. Okay, and obeying now the law of reflection. So if this is IGC, then from the normal this will also be IGC, and this sin A by sin R will no longer work. So this critical angle is very important. Beyond this, the light that you send, there is no reflecting surface here. Notice, there is no reflecting surface. It's only refraction. Because when you send a light, it is going through this surface to the other medium all the time. But then at this critical angle, if you send this light, then it goes and then hits the surface and then gets reflected back into it. No light comes out of it. No light comes out of this surface. Okay? So this is called as the total internal reflection. Total internal reflection takes place when the incident ray has an angle IC, as an angle I greater than IC. So this TIR, total internal reflection happens when I, the incident angle, is greater than IC. Okay? Then no light comes out of it. All the light is reflected back into the medium itself. Nothing is coming out. You don't have a reflecting surface or something. There's no reflecting surface. You just change the angle, the light comes out. Then, but beyond this IC, then for any other angle, whatever angle it be, it's going to get reflected back, following the law of reflection. I is equal to R. But this R is the angle of reflection. Once this condition is met, then when R I say is the angle of reflection, not refraction. Okay. So why does it happen in this case and why does it not happen in the other case? Well, when light travels from the rarer medium to denser medium, this will not happen at all. Total internal reflection will not happen when light travels from a rarer medium to a denser medium. Why? Because we saw it. The angle of incidence is always greater than the angle of refraction. So, you can never get this to 90 degrees. So, before this gets to 90 degrees, this incident ray will get to 90 degrees. Because this R will always be less than I. That can never happen. But here, when light travels from a denser medium to a rarer medium, you notice that R is actually conditional. When light travels from denser medium to rarer medium, R is greater than I. So R could reach 90 degrees before I could reach 90 degrees. So as I keep increasing this, then we can still be less than 90, but then this refraction, the angle of refraction can become 90. So total internal reflection will happen only when light travels from a denser medium to a rarer medium. It can never happen when light travels from a rarer medium to a denser medium. So no total internal reflection takes place in air, okay? Because air, if you see, has the least refractive index, 1, and glass 1.5. So if light travels from glass to air, then total internal reflection can happen. Let me just say light travel glass, so total internal reflection, glass to air, yeah, this can happen. And then it can also happen when it travels from glass to water. Why? Because water is a rarer medium compared to glass. This refractive index is 1.33 and this is roughly 1.5, different. Okay? So this can happen. From glass to water. And from water to air. It can happen when light travels from water to air. In that interface, this can happen. Okay? It will never happen the other way. In opposite directions will never happen. I want you to understand this. And there are certain materials which are listed in your textbook. Okay, then how do you find the critical angle? This IC. For example, like you have water and then air. And how do you find the critical angle first? Well, we know this. Okay, I'll use red because you should always go from denser to rarer. So I'm going to use red. Okay. So you know that sin I by sin R is equal to 1 by mu 2 1. That's important. This is the refractive index of glass with respect to air. But if I'm going to use this, it will be, what we're doing is refractive index of air with respect to glass, which is 1 by this one. So when I have this equation, I will take the refractive index of glass here, 1 by 1.5. That's what I get. Okay. So now, at the critical angle, what happens to R? Okay, when I is equal to IC, the critical angle, and then R is equal to 90 degrees. Okay? From the normal, it has come to 90 degrees. So then sin R, so that results in sin 90 is equal to 1. So note here, then sin IC is equal, because sin R is 1, right? Sin IC is equal to 1 is equal to 1 by mu 2 1. So in this case, if we take air glass interface, then sin IC, just an example, this is an example, okay? Sin IC is equal to 1 by, what is the refractive index of glass with respect to air, and is 1.5. Okay. So that gives you IC is equal to sine inverse of 1 by 1.5. And if you do it, you are going to get an angle of about 41 degrees. Okay? IC in this case, okay, IC in this case will be about 41 degrees, approximately about 41 degrees. So what it means is that inside the glass, light travels along the normal, it will come out. And then at 10 degrees, it will come out. So then to make a bigger angle than 10 degrees here, right? 20 degrees, it will come out. 30 degrees, it will come out. 40 degrees, it will come out. Then about 41 degrees, it will graze this. And if you have anything more than 41 degrees, then what happens is that it will, total internal reflection will take place and no light will come out. So you keep doing this, you will be able to see the light here. The light will appear to come from inside. Then keep changing it. When you reach 41 degrees, then you go slight. Then you will still be able to do that. But go just beyond that 41 degree, and total internal reflection takes place. You won't see any light here at all. Okay, so that is important. So I want you to understand it. So one more thing is this. When you see light here, where do you think the object is? Carefully, listen carefully, okay? Watch carefully. See, here, when you send the light like this, then the source is here. This is where the source is. So this is the source, light source. Okay? It will go here, then get refracted, and light will go like this way. Then you are seeing it here. This is your eyes. Okay? So this is your eyes. So you are seeing this. So you would think that the source is here. When you see things at this angle, you will think that the source is actually here. But the source is not. But that's how it will look to you. That's how it will appear to you. Because for you, this is a straight line. The straight line will go and it will be here. So your eye will think, or you will think, that the light source is here. But actually the light source is here. So this has sent this ray, and that ray has deflected, and it is going at this angle and reaches your eye. So your eye will think that the source is here. So that's a detail. Okay? But the source is actually here. Okay, that's something that I want you to understand. Okay, coming back to this. So each medium can have its own critical angle, because each medium has a refractive index. Then the critical angle is simply sine inverse of 1 by that refractive index. Okay. So when you talk about refractive index, you're saying that the refractive index of glass with respect to air, refractive index of water with respect to air, refractive index of diamond with respect to air. So this is what you see. Okay, so it's always, the medium acts as a second medium. When you define the refractive index, the medium acts as a second medium generally. Okay. When you reverse it, then it will be different. Then refractive index of air with respect to glass, but you don't do it normally. When you say refractive index, it refers to this particular medium, and this medium is always considered to be the second medium. So because light travels from air into that medium. So we are going to use this, and that would be always 1 by this, right? Because here this gives you the other medium. It gives you the refractive index of air with respect to glass. But what you have is refractive index of glass with respect to air, and that is why you have 1 by mutual here. Okay. So IC, the critical angle IC is equal to sine inverse of right here. So in this case, a simple formula for this will be this. So IC, the critical angle for any medium, is equal to sine inverse of 1 by the refractive index of that medium. Because the refractive index of the medium is found out by keeping the medium as a second medium. Okay, so that's why you get this. So for glass it will be 1.5, for diamond it will be 2.4. Okay. And water 1.33, like this. And there is a table in your textbook that tells you what are the different refractive indices for different materials. They have given you about 4 materials. The first one is water. For water, the refractive index of water is 1.33. Okay. The refractive index of water is 1.33. We'll write it down. Okay. So the refractive index of water is 1.33. Then the critical angle of water is 48.75 degrees, roughly 49 degrees. So if this is water, 49 degrees you will reach the, 48.75 degrees, you will, this angle of refraction will be 90, and any greater angle will result in the light being reflected back into the water and not entering the other medium. Okay, so that is it. And then for crown glass, this is glass within crown glass, one type of glass. The refractive index is 1.52, and then the critical angle for that is 41.14 degrees. And for flint glass, this is also glass, but then this is flint glass, dense flint glass. The refractive index is 1.62, and then the critical angle is just 37.31 degrees. So just go beyond 37.31 degrees and the light will get reflected back into the water. And when it gets reflected back into that medium, then the angle of incidence will be equal to the angle of reflection, just like the law of reflection. Refraction won't even take place. And for diamond, it is mu diamond is 2.42. The refractive index of diamond is very high. Okay, so the critical angle for diamond is again 24.41. See, so diamond is actually, the critical angle for diamond is very low, and that's the reason why the diamond glistens. Okay. So light that goes in gets reflected internally, and you get to, depending on the cut, like the why diamond glistens is also because of the cut and stuff. Okay, but the high refractive index of diamond is the reason why it sparkles. We'll talk about that a little later, but you can see that at this very low angle of 24.41 degree, then light won't come out. Light will be trapped inside the diamond itself. Light won't come out. But for all the other things, like you got 48.75 and then 48.75 for water, and then just 24, just half of it for diamond. So that's why it sparkles. So you have a table like that, go through the table too. So this is what happens. So for total internal reflection to take place, two conditions have to be met. The first condition is that light should travel from a denser medium to a rarer medium, not the other way around. Should travel from denser medium to the other way around. That is condition one. Second, the angle of incidence must be greater than the critical angle. Then light will get reflected back into the medium itself. It won't go out of the medium. It will be totally reflected back. Okay. And this critical angle can be found out using the refractive index of this medium. Hope this is clear to you. I want you to go through a couple of demonstrations which I've taken from the internet of total internal reflection. These demonstrations will give you a good idea of whatever we've discussed
Demonstrating optical phenomena in the classroom can be difficult. The trouble is, light beams are invisible. The normal scattering agents such as chalk dust are messy and can cause other problems in the classroom. The laser viewing tank allows students to see and manipulate light beams in a lab group setting. These tanks act as student workstations, so you can set up a bunch with little time or fuss. When I aim a laser into the tank filled with pure water, the beam can barely be seen. When I add a small amount of scattering agent to the water, the beam becomes highly visible. Some light is reflected from the agent's particles as the beam passes through the water. And we're going to dim the lights so you can see what's happening. Next, I'm going to aim the laser down toward the water at an angle to see refraction in action. Look how the direction of the beam changes when it enters the water. Set the tank at the edge of the table and aim the beam upward to see refraction again. If you increase the angle of incidence by aiming the beam through the water from the side of the tank, you will observe total internal reflection.
The knowledge of the total internal reflection helps you to understand a few phenomena that happen in nature, and also to use this knowledge for your advantage. For example, since we know what causes this total internal reflection, we can make instruments like this, like binoculars. Okay. If you think about it, when you look at an object through a telescope, it is always upside down. Okay, but when you look at objects through a binocular, the objects are not upside down. They are as they are. They are not inverted. But when you look at objects through a telescope, they look inverted, upside down. And why the images are erect in binoculars but not in telescopes is because binoculars like this use the idea, the concept of total internal reflection here. I'll explain that to you a little later, so that you get the erect image. And the fiber optic cables use the total internal reflection principle. And the other things that happen in nature, like mirage, can be explained using the total internal reflection. Also, a diamond, we just discussed that. So the natural diamond, it's not sparkling. But when you cut the diamond in a certain way, then you can make it sparkle. So the reason why the diamond sparkles is because the way it is cut by the diamond cutters. Okay. So that's like the knowledge of total internal reflection, as I said, can explain a few phenomena which happen in nature. And this knowledge can help you to devise things which are advantageous to you, like binoculars and fiber optics and stuff like that. Okay. Let me start with the mirage. Let's see what mirage is and why it happens. Let me take the picture given in your book is that of a tree, and I'll start with that. We can do anything, but let me just. Okay, like you have a tree here. Okay, so trees like this. This is ground. Okay, so you stand here. You stand here. Let me just take a leaf here. Okay, in this tree. Let me just take the tip. So that light from that point will go in all directions. Okay, so light will go here, 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 and then will come here, come to your eyes. So you are able to see this. Okay, from that tip. Okay, so you are able to see that. And the light will go here, hit the ground, go here, hit the ground, go here, hit the ground. It will go in all different directions. So the light that reaches your eyes helps you see the leaf. Okay, so this is what happens when you look at something. When you look at, I'm looking at the fan now, so that's exactly what is happening here. And then when you look at the tip of the fan, the light from the tip reaches my eye. Then I'm able to see it. So that's what happens. So it doesn't mean that there is only one ray, since it sends rays in all directions, right? So some of the rays will go and hit the ground also. Okay. They don't reach my eyes, so I don't see fans there. So what happens is, suppose you take a very hot day. On a very hot day, the ground is going to be really hot. Okay? So this is the ground. It's going to be really hot. It's a hot day. Like in a desert or something. Okay, so very hot. Just after noon. Okay. So this light is going in all different directions. So the ground is hot. Because the ground is hot, the air near the ground will also be hot and it will be less dense, right? Because it will try to rise from the ground. It gets heated up more quickly and more than the air here, so it will try to go up. So it is less dense. The air here is less dense. Here. Okay, less dense. Okay, rarer, I'll say it's rarer, right? Less dense meaning this is rarer than this air, which is denser. And this will be denser further, right? The top would be like optically denser and physically also this denser. There is hotter here, so this is rarer, denser, more denser. That's how it is. So now you see light comes from one of the rays come here. Okay? So it is like this. There are different layers now, right? So this is denser. Like that. Okay. So it comes here. Light has entered. Now denser. Now this is more denser, right? More denser. From here, it enters into the less dense or rarer part of air. So what will happen? So this would be this is interface. This interface is a normal, it makes an angle I and it gets into this part of the air, which is rarer air. Then what will happen? It will refract like this. Just use this for you to see. Okay? So it will come here. Then at the interface, this will undergo refraction. Then you see it won't travel straight like this. Now it is going to go away from the normal. Right? So it will go away from the normal. See, light now has bent. Now then you get into the rarer, even rarer part of it, and it will bend like this, and then it will get into, you see the angle is changing. You see the different layers, the angle is changing. Here maybe it was 30 degrees or so, now it will be 45 degrees, and then maybe 48 degrees or something. You see the angle is changing at different levels. So now at some place it's going to, it is maybe here, it's going to cross the critical angle. The angle could be more than the critical angle. If it's more than the critical angle, then it won't go hit the floor, but then it will get reflected off of that interface and get reflected here, and the reflected ray will also do this stuff and then it will come here. So you see, then rather than going straight and hitting the floor, then it's going to have a curve like that and will reach here. So what you would see Now you will see two images, right? Two things. One, the ray that comes to your eye directly, so it will look like this is, you will be able to see the leaf straight away. Then there is another ray that reaches you here. Okay, so that would be like this. Okay, if I take that, then I need to draw a straight line here, right? So it will look like, you know, I've not drawn it to scale, it will look like you have the leaf here also. Because this ray, even though it is coming from here, it has gone and then went and then it is reaching your eye, but because it is reaching your eye like that, it has come and it is bent and then it is reaching your eye. But you don't see it like that. For you, it's there. That's how you will see it. So you have another image here. Okay, so it is like you are able to see the reflection of this leaf on the ground. You see that the leaf is here, and you'll also be able to see the leaf. It's like this. I see the fan straight away. The blade can be seen, but if I look down, then I will be able to see the blade there also. So it's like a reflection. I think there is, you know, water or something which reflects that. Then why would I see a blade there? Unless it is reflected. It's like tube light, right? Like you have a switch on the tube light, and you can see the tube light directly, and the light can also get reflected off of the floor. You will see the image of the tube light on the floor also, right? It is something like that. But then it is reflection. It's proper reflection on the surface. If your house or classroom is pretty smooth, granite flooring, then you can see the image of the tube light there, because it's getting reflected from there. But here there is no granite flooring, but you will still be able to see. It's because the light from there, which is supposed to go to the ground and hit the ground, is now bent and reached your eyes. But for you, the light is coming from there. So you will see an image on the floor. So you think that maybe there is a mirror or water from where it's getting reflected. So this is what is called as a mirage. There is no water, but because of this reflection, you will think that there is water. So there is a tree there, and then I am seeing an image of the tree on the ground. Water. It looks like water. So where there is no water, you will tend to think that there is water. Okay. So this is how mirage takes place in your brain, in your eyes. Because the light which was intended to go hit the ground is now bent and it is reaching you like this, and you will see the object like this. The object to be here. So there is the object you can see here, and you can also see here. So you think that that's obviously, you know, that there can be no leaf on the ground. There can be no tree on the ground. But why are you seeing it? It's because there is some kind of reflection, and you think it's water. So then people go chase this water, and it will keep going. This is something that you have observed, you know. So on the road itself, like particularly if you have traveled on highways, you can have this, you can see this phenomenon. The reflection of buildings and stuff on the road can be seen. But it looked like that part of the road is wet or something. So this is mirage. To explain the phenomenon better, I have drawn this picture. Okay, so this picture has different mediums layered one on top of another. Okay, so D1, D2, D3, D4, D5, mediums of different optical densities. Okay, so D5 is greatest. D5 is the densest of all. D5 is greater than D4, and that is greater than D3, and D3 is greater than D2, and that is greater than D1. So this is how it is. So it's denser, less dense. This is the densest, then less dense, even less dense, even less dense, and that is how it is. Okay. So now let us take a ray which hits this interface between D5 and D4. So I can have a normal there. This is a normal at the point. If this was not there, this would have continued along the dotted line. Continued along the dotted line. Okay, so it would have gone like that. Gone like that. Okay, but now you have D4, so less dense. So it is like coming from glass to say water or something. Okay, or glass to air, however it is. So now, when you come from denser medium to rarer medium, then you can see that instead of going straight, it's going to bend away from the normal. Okay, now it hits here, comes and hits here. After this deflection, it's a deviation, it comes and hits here. You see this angle is I5, let's say. This will be I4. Okay, but I4 is now greater than I5. So this angle is increasing. Now, if this medium was not there, this D3 was not there, then this would have continued along this direction. But D3 is there, so it will undergo refraction. And it will go away from the normal. So it will continue here. And it will hit this position where you have the interface between D2 and D3. Okay. So this is going to be my I3. Notice that I3 is greater than I4, which is greater than I5. So the angle is increasing all the time. But suppose this I3, that is more than the critical angle for this medium, D3. If it is more than the critical angle for this medium, then it will reflect back. It won't pass through it. The total internal reflection will take place here. Then this will go this way, and you are going to go from this medium, which is D3, you are getting into D4 now. Well, you know that D4 is denser than D3. The greater the number, the denser it is. It's denser. So it is like going from air to glass or water. So now this ray will now bend towards the normal. Here, as you travel from here, D5 to D4 or D4 to D3, then the ray will bend away from the normal. But when it travels backwards from D3 to D4, then this will bend towards the normal. So from here again, if you take this should have gone straight, but then you have this interface between D5 and D4, so it will bend towards the normal. See, this is how light will travel. So the light which should have gone straight here is now here. Okay? So a guy who is looking at this light will think that this source is here, whereas the source is here. So I want you to understand.